little loud even maybe. All right, so I will be talking about building database management systems in Scala, and the subtitle of my talk is how types can turn a SQL interpreter into a SQL compiler. So before we start, there's one little disclaimer here that I'm not making any product announcements on behalf of Oracle, but just presenting ongoing research here. So I would like to start with the following quote here. So many people have said that any problem in computer science can be solved by adding another level of indirection. And the quote is usually attributed to David Wheeler. But what many people forget is that this quote actually has a second part. So any problem can be solved by another level of indirection, except problems that are caused by too many levels of indirections. And those problems are usually performance problems. And more generally, there is a big trade-off when we build systems between generality and specialization. So on the one hand, we want to be very general in the systems that we build. In particular, if you look at data processing systems, we want to have systems that work for many kinds of data and for a variety of processing tasks. But on the other hand, we need to specialize to get good performance. So we need to specialize with respect to data schemas, with respect to whether we are running analytical or transactional workloads, and we even need to specialize to our hardware platforms, right? Whether we're running on a single box or on a cluster of machines, or maybe we have GPUs or SIMD architectures that we want to target. So what are the challenges in data processing right now? Well, the biggest thing is that the workloads change, right? So everybody is aware of big data, and that usually is taken to mean like we have more data, we have more different kinds of data, and data is coming faster at us, so we need to process things in a more efficient way. The other thing is that hardware changes, right? So it used to be the case that database systems were mostly disk-based, and disk I/O was the main bottleneck. And this is fundamentally changing since systems are moving more towards an in-memory processing model. Right? So systems need to adapt to these changing requirements here. And these problems are well known in the database community. But the issue is that popular generic database management systems consist of upwards of 1 million lines of optimized C code, and in some cases even tens of millions of lines of code, right? And how do these systems get so big? Well, actually, because there is a lot of specialization for performance reasons, right? So we actually looked at PostgreSQL, and you can find like 20 different implementations of a memory page abstraction, which fundamentally does do the same thing, right? But they are just specialized to get better performance. And there are about 7 implementations of B-trees here. So all this manual specialization and big code bases make these systems very difficult to adapt, right? So now we're switching from disk-based to memory-based systems. So we need to change all these millions of lines of source code, right? And that's not very easy to do, right? It takes a lot of effort and yeah. But the other point is that even with all this manual optimization and specialization, these general purpose systems are still like 10 to 100 times slower than if you just go and write a particular SQL query by hand in low-level C code, right? And prominent researchers in the database community even argue that, well, these generic systems, it's an idea whose time has come and gone, right? So we need to build specialized systems, and some people say that, well, it's time for a complete rewrite here. But now it's interesting actually why there is such a performance gap between like manually written code and what general purpose systems can execute. And the main reason is that most existing database systems, you have SQL queries coming in and they are optimized on a high level. So you change the order of joins, you take selectivity of predicates into account and come up with an optimized query execution plan. But then there's an interpreter which interprets this low-level query execution plan. And this interpreter is usually written in such a way that it's really like, okay, get me the next tuple from a relation, get me the next tuple, then evaluate some predicate on this tuple and maybe store it in some temporary hash table, but then get me the next tuple, right? So it's very, 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 there's a lot of interpreted overhead for each individual tuple that is processed, right? And sort of coming from a compiler and programming language background, it's immediately clear that whenever you have an interpreter somewhere, you can get better performance by using a compiler instead. But the sad thing is that, well, developing compilers is much harder than developing interpreters usually, right? And there have been some projects recently looking into query compilation for database systems. most of them are based on LLVM. And if you're a little bit familiar with LLVM, then, well, you can do amazing things with it, but it's also a very low-level programming model, right? You have to really program a compiler and reason about things on the level of basic blocks and virtual registers, which is a very different abstraction level than reasoning about things in terms of joins and maybe hash indexes. So I would like to talk a bit about a project that I've been involved with. So it's a joint project between Oracle Labs and the database group at EPFL, led by Professor Christoph Koch. And we developed a small database query engine in Scala. So we take optimized query execution plans from the Oracle database, and then we use meta-programming techniques to compile these query execution plans to low-level C code at runtime. And our little system supports all 22 queries from the standard TPCH benchmarks in just about 3,000 lines of Scala code. And the point we're making with the system is really that it is indeed possible to write high-performance systems code in a very high-level language such as Scala. So what's the kind of performance we get from the system? And here's a little graph. So we're comparing, so the DBX is a commercial in-memory database system by a large vendor, of course. And we're comparing Lego-base and another system which is called Hyper, which uses LLVM to compile query plans. And you can see that, so these are speedups. So DBX is one here. And you can see that Lego-base gets very good speedups on basically all queries in this benchmark set, right? So it's on average, it's almost an order of magnitude, and for some queries, it's even like 20x or something like that here, query 13. And you can also see that our system is faster than Hyper on all of the queries that we have here. So how do we achieve this? Well, we have a secret weapon. And the secret weapon is called LMS. It's short for Lightweight Modular Staging. And it is an extensible compiler framework that is implemented as a Scala library. And basically, we use the Scala type system to make a distinction between values that are executed now at compile or code generation time and types which are compiled and then executed later. And this allows us to specialize and compile program pieces at runtime, and we can use the full Scala language to compose things and generate very efficient low-level code here. And what I like about this project is really that we're taking these core programming language ideas of meta-programming and applying them to a different field in computer science, namely databases. And well, I guess you all heard Eric Meyer's keynote, and he was talking about denotational semantics and how compilers are not fundamentally more difficult than interpreters. And of course, database people are not really familiar with these concepts of denotational semantics, right? So the nice thing here is that we actually had an impact on the database community. And now our collaborators are writing these manifestos, basically saying, look, we should use these high-level languages in systems development, right? And there are things in there like have the cake and eat it too. And the main thesis of this article is that databases implemented in high-level programming languages can beat state-of-the-art databases implemented in C performance-wise, right? Which is something that is not obvious and not something people in the systems community are ready to believe, really. So I mentioned earlier there's this big trade-off between generality and specialization. So what we really like to do is we want to program in a very generic way and run specialized code, right? So how can we achieve that? If we just have a generic program, then what do we do? And the key idea is that we turn this generic program into a generic program generator. So we kind of perform this Aikido move of using our opponent's strength to our own advantage. And instead of having this cost of abstraction all the time during execution, like for each tuple in a table, we incur this cost only once, namely while we're generating code. And this means actually that we're using indirection to solve performance problems too. So this brings me to the concept of staging or multi-stage programming. And this goes back to an old observation really already from the 80s or even before, that most programs and computations can be separated into stages, which are distinguished by frequency of execution. So some parts in a program are executed more often than other parts, or by availability of data. right? So some pieces of a program are only executed after a certain piece of data becomes available. Like if you think about databases, maybe the schema is known, and then later the query becomes known, right? But we can optimize the query based on the knowledge of the schema, because we know that the schema won't change during the query. And the idea of multi-stage programming now is to make these stages explicit in the programming model, right? So in general, we have facilities to delay expressions to a generated stage. We have the ability to run delayed expressions, and in general to treat staged program fragments as first-class values. So how does this look in Scala? I already mentioned the LMS framework that we've been building, and the idea is to encode the staging informations in the types. So whenever we have a regular type T, like int or string, this just means execute now, right? So there's nothing to it really. But whenever we have an expression of type rep of T, like rep of int or rep of string, this means that we will generate code to execute this expression later. And the whole thing is implemented as a library in a rich language, in this case Scala, so it's not baked into the language or Scala compiler, and hence we call it lightweight. And the staged language, so the operations we can perform on code fragments, are just defined by library methods. So this is why we call the framework modular. So let's go through an example of how this works. So here's some code a programmer might have written. So it's just these 3 lines. So there's a print line statement, then we have a value myString, which is computed by some expression that produces a rep of string. And then we're going to print the length of this variable myString. So first of all, in LMS, we have an interface definition here. So we have a higher kind of type, rep of T, which is like completely abstract. It's just a marker here. And then we just define methods. So here we use Scala virtualized to define an infix method. We could also use an implicit class here. That doesn't really matter. But the important thing is that all the parameters are now these rep values here, right? So infix length takes a rep of string and produces a rep of int. So that means it's going to be a staged expression for which we generate code. And println is also redefined here to take a rep of any and return a rep of unit. So this is the interface, and for this interface there needs to be a suitable implementation, right? And in the implementation we actually have a hierarchy of IR node types, right? So we say that a rep of T, we define it inside this piece, so it's all like the cake pattern, right? And in this piece of the cake we define that rep of T equals expression of T. An expression of T is either a constant or it is a symbol that can refer to other IR nodes. And then we have case class definitions for individual IR nodes. So we have string length and println. And then we define these methods from the interface, like infix length and println, to create expressions, to create IR nodes that represent these expressions. And you can see that in the definition of infix length, we can already do some simple rewritings here, right? So whenever we want to compute the length of a constant string, then we can just return a constant that captures the length, right? And let's go through what happens when we execute this code. So first we execute the println statement, and what it will do is it will invoke the println method at the bottom. And here we have this reflect effect call. So this is an internal API call which says, okay, we have a statement that has some side effect here. And what will happen is we create this reflect print node at the top, and we assign it a fresh symbol, right? So this becomes a node in our IR graph. So the second statement will compute myString. The result will also get a fresh symbol here. And then we execute str-length. And here you can see we are introducing a dependency, right? So str-length refers to the previous result by its symbol, which in this case is 45. Then we execute the second println call. And since this is also an effectful statement, we're introducing effect dependencies here. So there's first a data dependency to symbol 46, which is the string length. And then there's an effect dependency to the previous println. Right, and these effect dependencies make sure that actual statements are not reordered or duplicated in the generated code. So given all this infrastructure, how do we work with that? And there are a few interesting programming patterns really here that we're using. And I'm going to present 3 of them, or sort of mention them as we go through some data processing code. So the first is what we call deep linguistic reuse. So that means that we can reuse facilities of the meta language, so regular Scala features like higher order functions, objects, and classes, in the programming model to compose code fragments. But this functionality does not end up in the generated code, right? So we want to generate code which is low level and consists only of arrays and while loop and whatnot, but we can still use higher order functions at the Scala level to compose these pieces of code, right? So I can have a for each abstraction which takes a closure, but still what I generate is just a while loop, because essentially things will be automatically inlined whenever you have a function that is not a staged function itself. Another important thing is that we can build mixed stage data structures. So we can build data structures which have like parts that are evaluated at code generation time and other fields which are generated code values, right? So we're going to see an example for that. And another very important pattern is that we can, whenever we write an interpreter, we can specialize it with respect to the program. And that means that our interpreter really becomes a compiler when we add these wrap types. So let's do an example, some actual data processing code. So instead of actually loading data from tables or something, we're just going to look at CSV files here, right? But the principle is basically the same. So CSV file, here's an example on the right. So in the first line, we have the data schema. So we have the column names. And then in each line of the file, we have essentially a data record, right? So we comma-separated values here. And the way we might want to work with this is just have this process CSV abstraction here, which takes a file name and then a closure that's invoked for each line in the file, right? And we would like to have records as objects, which we can query by name, right? So we want to say, for a given record, give me the flag field and compare it to yes, right? And if this is true, then, well, I want to print the name field of a given record here. Right, and this is how we can implement this in Scala. So there's just this record class, and it has an array of strings for the fields and an array of strings for the schema. And whenever we look for a key, then we find the index of the key in the schema and access the field array at the same index. Right, so no surprises here. And the process CSV method is also pretty simple. So we just like open the file, then we read the first line that gives us the schema. And then we go through all the lines and we invoke the callback on a newly created record object that we have created from the fields and from the schema that was read from the first line here, right? So obviously, I mean, this code is gonna work, right? And it's nice to write. It's just a few lines of Scala, but performance is going to be really bad, right? I mean, even if the by name lookup of fields is not optimized here, so we're just using index of, so it's a linear time operation, right? So high performance code looks really different, right? But given this little process CSV abstraction, we can build more interesting things on top of it, right? And so now we are really going towards something like a database system. So we want to parse SQL statements, right? So here's a select statement coming in, and it just does the same thing that we had on the slide before here, only that it's expressed on an even higher level of abstraction. And given facilities that we have in Scala, like Parser Combinators or another library, we can implement a SQL parser. It's also not too much work, and introduce essentially a hierarchy of classes which correspond to these query operators here. So from the SQL statement, we are building this operator tree here. So at the leaf, we have a scan operator, which just takes the file name, and then there's a filter operator, which takes an expression that evaluates the predicate here. And after that, we have a projection. So we want to just get the name field. And at the end, we want to print out the result here. So how do we implement this? Well, we write a little interpreter, right? So we have this exec method here, which takes an operator and, again, a closure. And our scan operator is just calling the previous process CSV method that we had before, right? So this is all pretty simple. And just in the same way, we can implement the other operators here. So filter just calls the parent and has a condition in the closure here, so that we continue like down the line only if the predicate is true. Projection just works on the fields of the array, and print, well, it just calls print line, right? And of course, we also need an evaluation function here, which evaluates predicates for a given tuple. So now we have this little query interpreter. Well, and if we run it, it's going to be even slower than just calling process CSV itself, right? Because we always have this dispatch overhead for filter and project, etc. And each predicate is now interpreted, right? So it's no longer just Scala code that's executed, but it's really going over this tree of expressions all the time. But here's sort of the secret sauce. So we're going to turn this interpreter into a compiler by applying staging. And the idea is that, well, staging is a process that generates code, right? Or IR structures in our case. And what's an interpreter? Well, an interpreter is kind of the dual thing, right? So an interpreter takes code and some input and produces a result. So we can actually put these pieces together. And this means that we're splitting the input. So we take the code and we make the input symbolic. So we just give it symbolic names as placeholders, and we stage our interpreter. So our interpreter, the staged interpreter, now takes symbolic input and code and produces faster code, right? So it generates code that we can then execute on the actual input to get the result here, all right? And well, we can do this for essentially all kinds of interpreters. So for example, one thing we looked at was regular expressions. So in this case, the code is the regular expression here. So AB star at the beginning of the line. And the symbolic input is just a variable of type rep of string. And the code that is the result of this that is the output of this staged interpreter that we're generating for this particular regular expression is really Scala code which implements the regular expression, right? So it takes the first character of the input, sees if it's A, and then takes the next one, sees if it's B, and tries to match as many B's as we can, right? So it's really low-level code that implements this particular regular expression. And of course, we can run this code on some actual input and then get the result of the regex matcher here. So let's apply this idea to our little data processing engine here. And it turns out that we don't need to change many things, right? So here's our generic library implementation. And if we want to stage it, then basically all we need to do is this. So we need to change in the definition of the record class. We need to change the fields array from array of string to rep of array of string. And now here's something interesting, because records are now a mixed stage data structure. So we have static parts, the schema, we haven't changed that, and the fields are now dynamic values. So what does that mean? So that means that we never generate code that works on records, right? So we don't have rep of record anywhere, but we just generate code that works on the fields of records, right? And all the computation that only depends on the schema is completely evaluated at staging time, right? So the schema is something that is a completely static concept here. And the generated code is specialized to both the schema and the actual query and processing task here. So in order to achieve this, we need to tell the system when to compile things actually. So in the definition of process CSV, we introduced this run block, which says, okay, compile the query processing code after loading the schema. Right? So we can do that only once we know the schema and once we have read the first line from the file here. And actually, to make this file reader available in the generated code, there's a special operator we need to use, which is called static data. Right? So this is called cross-stage persistence. So we need to take an object from the present stage and make it available in the generated code as well. So given this code, we haven't changed much, right? But what is executed actually changed quite a bit. So the code that is actually executed looks more like this, right? So all the gray parts really go away because we are specializing on those things. And really what happens is that the run block is you can think of it as being inlined here, right? And the closure that we have been passing, which does this evaluation of these predicates, is inlined there as well, right? And instead of accesses of record fields by names, we just have numeric accesses here, right? So where we previously had something like look for the flag field, this is just becoming fields 2 here, right? And name becomes fields 0, because all the schema computation has been evaluated at generation time. So the effect is essentially what we like to call abstraction without regret, right? So we have built this this interpreter structure and this high-level data processing things, and we're working with objects like records, etc. But we don't pay a price for this abstraction in terms of runtime cost, right? And yeah, so here's the things that we've been using. So we've been relying on deep linguistic reuse. We have been using staging time functions, so functions which take a rep of A argument and return a rep of B, right? And that's a crucial difference to a staged function, right? So a present stage function that takes a rep of A and returns a rep of B is just essentially a transformer. So it's not a function that ends up in the generated code. Whereas if I have a function rep of A to B, then we would generate a function in the IR here. We've been using these mixed stage data structures, in particular records, and we relied on the fact that if we stage an interpreter, what we get is a compiler, right? And actually, given what we did here, there's nothing else we need to do for the interpreter code, right? Which interpreted SQL statements. So we can just use this pattern here, and our interpreter sort of also just goes away here, right? So even if we give it this operator tree, what is executed in the end is exactly the same code here. Now we can take these ideas even another step further. So we've seen that any staged code produces an IR, and we know that staged interpreters are compilers, right? So now we can do something interesting, and we can implement an IR interpreter. So over the IR that we've been building in the staging process, we can interpret it again using a staged interpreter and get another IR here, right? So the key takeaway here is that a staged IR interpreter is actually a program transformer. And now we can do interesting things, namely we can build these pipelines of IR transformers, right? And at the end of this pipeline, we can generate some output code here. And this is like a crucial difference. So we can use this to implement like multipass compilers, but there's a crucial difference to like regular compiler technologies, right? So if you look at how most compilers are built, then it very much follows the old techniques from the 70s, in that we are working directly on tree or graph representations, right? If you want to do a compiler, if you want to implement a compiler transformation, you need to say, well, here's my input expression tree, and I'm transforming this like piece by piece into another expression tree, right? Whereas here, we're just implementing interpreters, right? So we have to, when I have a high-level expression at the first stage here, then I just need to define what does this mean in Scala code, right? And then I can stage this Scala code, and I get my transformer essentially for free here. So if we look at how general purpose compilers normally work, then it's really this kind of bottleneck here, right? So there's a large design space in things that the programmer wants to express, and there is quite a bit of variety in terms of hardware. But going through this general purpose language, it really means that we're losing information, right? So what we want instead is something more like this. So we want to have something like a high bandwidth compilation pipeline where we can do optimizations on different abstraction levels and also extend the system in many different ways. So if we look at what we did in Lego Base, then there's a couple of layers really here, right? So we start with something that is very high level and directly corresponds to these execution plans we get from the database. So the objects we're working with are like operators like scan, join, and project. And then what we do is we translate them down using staged interpreters to something on the level of hash maps and records. right? And then there's a set of optimizations we have on this level, right, where we need to look at things like indexes and what are the types in records, etc. And once we have done optimizations on that level, we translate things down to an even lower level, which is basically just primitive arrays, loops, and pointers. And in addition to these specific optimizations, we also have generic optimizations on each level, right? So we can do common sub-expression elimination for things that build hash maps, for example. And this is very interesting. So here's one example of the kind of optimizations we can do. So here's a SQL query, and you can see it's a nested query. So there's a nested select statement, which performs an aggregation. Right, and there's actually a few aggregations here, so there's 3 sums, and one thing you can see here actually is that there are some common sub-expression in these aggregations, right? So for example, this 1 minus s dot b is evaluated multiple times here. And if you look at this query, then you can see that, well, it's really important to look at this thing as a whole, right? And what a regular database system would do is it would have basically templates for each of these aggregations, right? So there's a template which says how you evaluate a sum, right? Or how you evaluate an average or something like that, right? And even if you have a query compiler that you're building using LLVM or something, then most systems follow this kind of template approach, right? So you would have a template which says, okay, here's how a group by looks like, and then maybe I can put in some pieces and replace some, fill some holes with other LLVM IR code that I generate, right? But one thing we can do using our approach is really by this successive lowering from operator statements to things that work on arrays and hash maps, etc. We can treat the query as a whole here, right? So in the end, there's no problem in applying generic common sub-expression elimination on these like nested aggregates, because it all ends up in one piece of generated code here, right? So it's immediately available on the IR level to see that here's actually something that is computed multiple times. Another interesting thing is here, if you look closely, that so we first perform this group by, right? And then we perform a join. And we're actually joining on the same key as what we're grouping on. So if you looked at how this would be implemented in a naive way, is that, well, a group by creates a hash table, right? And it hashes things by this key, and then it accumulates the sum value in the hash buckets, right? And the result of this group by operation is this hash table, which maps keys to aggregate values. And then what does a join do? Well, chances are it's implemented as a hash join as well. So it traverses all these tuples that are the results from the group by, and it builds another hash table, right, based on the same key actually. And that's something you don't really need to do, right? If you look at the thing as a whole, and not only on individual operators, but on the whole query, you can recognize that you don't need to build 2 hash tables here. So one hash table is sufficient. And that's something we can also essentially do by pattern matching and common sub-expression elimination, that we see, well, here's something that can be reused between the operators, so I'm going to build this hash table only once, right? The third thing which gives us quite a good speedup is that instead of having generic data structures, right, like a hash table that works for all kinds of records, we can generate specialized implementations for a given schema. Right? So, for example, we can say, well, I have a field and it's a tiny integer, so it's maybe just 1 byte or 2 bytes. So maybe I don't actually want to build a hash table for this. Maybe I just want to build a linear array. If it's only 128 elements, then there's no point in doing hashing, right? I can just do a small array and use index lookup, and I'm always precise, right? So we can really specialize things to the given data types here. Whereas if you're just implementing a database system and maybe manually optimizing it, then some programmer will actually need to write all these implementations, right? And need to maintain them if requirements change at some point. So here are some more experimental results for Lego Base. And since we are generating things, we can also generate different variations, right? So we are not fixed to one shape of code that we can generate, but we can flip the switches and try alternatives, right? So actually, here's a few variations. So we're comparing generating C code versus generating Scala code. So those are the red bars. So the light red is generated Scala code, the dark red is generated C code. We're comparing again to Hyper, and we also simulated Hyper by basically doing all the optimizations they describe in their paper, implementing them in our system here. And we can also play with a push versus pull model of data processing, right? So what I showed in my CSV example here was really this push model. So you invoke a closure for every tuple, right? And the pull model would be the more traditional iterator thing, giving me the next tuple, giving me the next tuple, etc. And well, this is interesting because we can really compare the performance between these models, right? So here's comparing push versus pull, respectively for C and for Scala code. And you can see that, well, push is always faster, but for C code or Scala code, it's not really the same speed up here, right? So it seems to help more for Scala code actually than for C code. Right, and here's we can break down the speed up we get for each of the TPCH queries as well, right? And there's some interesting things you can deduce, like if you look at the queries, how many joins they are, what kind of join structure, etc. So I briefly want to mention a second project here, which has been done at the database group as well. So again, in Christoph Koch's group here. And the system is called DBToaster. And it's a query compiler for real-time analytics. And the basic idea is that, well, we don't want to do bulk processing on data, but we want to really work on incoming data and incrementalize our queries, right? And so the idea is that from the SQL statement, you're going to derive an update handler, right? So this is a piece of code that, whenever you insert something into this customer relation, then here's how you need to update some auxiliary data structures. And the goal is real-time analytics like policy monitoring, algorithmic trading, etc. So this system has been developed like over a couple of years. There was a VLDB paper in 2012. And the first prototype was written in OCaml, and it was about 16,000 lines of code. And it really showed great speedups over like implementing these incremental processing tasks in regular database systems, right? So you get several orders of magnitudes by doing this aggressive incrementalization over just recomputing values here. Now the interesting part is that actually we worked on building a new DBToaster backend using LMS. And the main benefit here really is, so first of all, we get additional speedups here, right? So you can see the original code, and then the LMS optimized code is quite a bit faster here, so several factors. But the main thing is that the reduction in code size is really drastic here, right? So down from 16,000 lines of OCaml code, we're down to just about 3,000 lines of Scala code, and we actually do many more optimizations than before, right? So you really get much more productivity by relying on this existing compiler framework. Another thing is that, well, data is not only stored, but it's also transferred. And the data transfer also needs to be efficient. So the third thing we did was implement a staged version of Parser combinators for communication protocols and data formats. So this is a project from Martin's group by Manohar Jonalageda. He's the main author. So again, the story is, well, if you look at efficient hand-optimized protocol parsing code, then it looks like this. So this is taken from Nginx. It's part of the HTTP parser, and it's really like more than 2,000 lines of low-level optimized C code, which implements this manually optimized state machine here, right? So what we did was, well, in Scala we already have parser combinators, so we thought, well, maybe we can stage parser combinators, and that actually works very well, right? So in just about 200 lines of code, we have a description of the HTTP protocol, And it's really easy to compose things, also like to change the behavior of a parser. So you can say, well, I'm not going to bother parsing all the headers here because I'm only interested in the payload, or maybe I'm only looking for a particular header. So you can really mix and match these things, right? As you would expect from parser combinators. So now let's look at performance. So the first thing about like regular parser combinators is that they are really too slow to be used for any real processing task where performance matters, right? So if we compare at the top, we compare HTTP parsing using the regular Scala combinators and Nginx. Then, so this is megabytes per second. Then the regular Scala combinators, they don't even show up on the graph, right? It's just too slow, right? But by adding staging, we actually get pretty close to Nginx, right? So we're about 200 megabytes per second, and Nginx is doing something like 300. And this is running Scala code on the JVM, whereas Nginx is like optimized C code, right? So we can also do JSON parsing here, and here we're actually a lot faster than JQ, which is an optimized C framework for doing JSON parsing. And you can also see that we are like, yeah, really quite a bit faster than Spray and Parboiled and other Scala frameworks here. Another interesting thing, taking this one step further, is that, well, since it's all combinators, yeah, we can build layered parsers as well, right? So if you look at HTTP, then there's these chunked HTTP responses, right? So you say, well, yeah, and some payload here. So in a simplified way, it looks like this. So you have an integer which says now you need to read 2 characters, and then there are the 2 characters, and there's another integer which says, okay, now you need to read 3 characters. So if you want to decode this, you would just get hello or helicopter or something like this, right? But you need to have these, yeah, you need to combine parsers for 2 protocols really to do this efficiently. And using combinators, that's pretty easy, right? So we just have this read chunked method here, and we can actually parameterize this over yeah, over a parser that parses the header. The only requirement is that it needs to get us a chunk size, right? And then we say, okay, read n bytes, which is the chunk size, and then do a recursive call, which starts over again, right? So the takeaway here is really that, well, the chunk parser can be unaware of the payload, and the payload parser does not need to know anything about the chunking, right? And still we can generate code which does the parsing in one single optimized pass here. So this brings me to the end of my talk. I just briefly want to mention like other projects and collaborations we've been involved with. So I guess the biggest project is Delight. This is together with the Stanford Pervasive Parallelism lab, and well, maybe some of you have seen Kevin Brown's talk. I guess Kevin is in the audience as well. And here the idea is really we want to use this runtime compilation techniques to build domain-specific languages for big data on heterogeneous devices, right? And we have great results on running stuff on clusters of machines and ship computation to both CPUs and GPUs on all the machines in a cluster. Another project we've been working on with Markus Pischel's group from ETH is Spiral. So Spiral is a program generation system for fast numeric libraries like fast Fourier transforms and linear algebra transformations. And Spiral also was developed independently over many, many years. And we worked with Markus Pischel and his students to re-implement the core of Spiral on top of Scala and LMS. And there we also used interesting programming techniques, like, for example, type classes. Type classes are very useful because you can dissociate the actual data from the operations, right? So you can build type classes that are completely resolved at staging time, yet provide functionality for dynamic values. So you can have like a numeric type class for wrap of int and wrap of double values here. Lego Base I already mentioned in the talk here. Lancet, that's a project I did for Oracle Labs, and the question here was, well, can we integrate these LMS techniques more into the regular JVM and JIT compilation framework? And it turns out that actually works quite well. So we just add a staged interpreter for Java bytecode in front of our processing chain, and suddenly we don't even need wrap types in our code anymore, right? We can just take regular Java bytecode and rewire certain method calls to do something more efficient here. We also looked at generating hardware instead of just generating C code. That's with another group at EPFL. I already mentioned the Parser combinators, and we also looked into using staging to generate JavaScript. Right? So this is a little different than Scala.js, because again we have tight control over the shape of code that we're generating, right? And when we can use like Scala features, to compose things and not pay the price in terms of code size or runtime cost here. So to sum up, I guess my main message really here is that optimizing compilation does not need to be hard. So I think it's easy and it's very powerful. So we should really embrace it as a programming pattern. And the second message really is that, well, I think in what we did shows that Scala can actually beat C as a low-level systems language. And with that, thanks for your attention, and I'm happy to take questions. Yes, please.
Is there any possibility that these LMS techniques gonna be part of a Scala standard library, standard compiler?
So it's independent of the Scala compiler, really. It's just a library. It's open source. It's on GitHub. You can download and use it if you want.
As far as I know, LMS uses kind of patched version of Scala compiler, isn't it?
Yeah, we have a few small modifications to the Scala compiler, but all you need to change in your SBT file is change your Scala group ID to orgs.scalalang.virtualized.
And how kind of up to date this is? Is it Scala 2.11?
So right now it's Scala 2.10, but we're working on 2.11 support.
And one more question: are there any connection to macro support? Is it related somehow?
So that's a very good question. So it's in one sense it's doing something similar, but the main difference is that macros work inside the Scala compiler, whereas what we're doing is completely at runtime. Right? And that has a few like trade-offs, right? So if you're inside the Scala compiler, what you can do is you can have like nice error messages at compile time, right? And if you're working in Eclipse, you can like have domain-specific messages and like have these red squiggles if there's an error, etc. Right? But on the other hand, if you're at runtime, then you can all these things that I showed, like you can read the first line from a file and then specialize your code, right? And that's something you fundamentally can't do if you're inside the Scala compiler at compile time.
Would LMS speed up the Scala React formulation of functional reactive programming?
Very good question. I would say probably yes. We haven't looked into that.
Could you just get verified? Could you, as a continuation of the previous question about macros, couldn't you get a code verification, the abstract syntax tree from a macro, and then use it at runtime to do what you're doing without even having to depend on the rep types?
Very good question as well. So I think the next talk by Vojan Jovanovic actually presents a system that combines macros and LMS in such a way. But again, there are certain trade-offs, right? So the question is like, if you just have an abstract syntax tree of this program, right, then there are certain things which become much harder, right? So here, just by using the types, you have these programming patterns, right? So you have mixed stage data structures and things, right? And if you don't have the rep types here, then the question is, well, what do you do, right? How do you identify these pieces, right? And